and I'm going to flip screens. And share it. Okay. So, right. So hopefully you can now. You've all got the. You can see the PowerPoint on the screens. Flight theory and instruments. Of course, I've muted you all to ask the question. Brilliant, John. Well done. So, right. So basically, the main thing to sort of arm yourself with is the. If you haven't got it, there's a copy of the syllabus which you can get from the BHPA, and as I would say, just use that as a checklist. Just work through each point. Use these notes. Use the pilot handbook, which you should all have. Pilot handbook. And between that, if you do both, go to the pilot handbook. It's unusual someone will fail the exam. So these are to act as a bit of a refresher. It's to go over some points. I can't guarantee it's 100% correct. I've tried to make it as accurate as possible, and I can't guarantee there's no mistakes. So if you notice something, let me know afterwards, and I'll update it. Anyway, so basically, we have to look at how wing creates lift, including the relevance of Venturi tube and the Bernoulli's theorem. So some of this you need to know. Essentially, I'll add some people as they turn up. Someone short arriving late. Right, so basically, the overriding principle is that total pressure within a fluid remains constant, provided the energy is neither added nor removed from the system. So if you have an enclosed system, the total pressure remains the same. Bernoulli basically says when air is passed through a constriction, e.g. a Venturi tube, its velocity is increased and its pressure is reduced, basically. So if you pass something through a constriction, it speeds up and its pressure goes down. So the basic reasoning for that, next slide here, come on. So you basically have two types of pressure. You have static pressure, like it's what you measure with a gauge, and you have dynamic pressure, which is what you feel if the air pushes against something. And it's the sum of these two which gives you your pressure. So you're balancing static and dynamic. So essentially, when we get onto good old Bernoulli, and you're passing, you're constricting, the total pressure is the same, basically. So by increasing one, you basically decrease the other. So by speed, you put it through a constriction, you are changing the sort of dynamic pressure, and you're changing the speed. So, but you don't have to get that technical. All you basically need to know is this: that when you go through a constriction, speed increases, pressure gets reduced. Oops. And another person arriving late. So, how does that relate to flying and wings? So let's come down a bit. So the basic thing is this: velocity increases and pressure gets reduced when you constrict the airflow. And you're, from a practical point of view, other than just wings, you'll see this on some of our hills, like Caban, where you've got a narrow constriction. The air compresses through it and speeds up. If you've probably noticed, if you've been flying and you're in a sort of tightening valley or gap of some sort, the airspeed picks up, you get blown back faster. And it's just this basic principle that the velocity is increasing. So now, without getting into a whole bunch of arguments about how wings work, basically what you need to know is that as a result of the airspeed increasing over the wing, the static pressure reduces, and this generates about 2/3 of the lift. So this 2/3 figure is what you need to know. Is how the lift splits. So as a consequence of the shape of the wing, the aerodynamics, the air flowing over it, you've got Bernoulli's theorem, reduction in pressure, 2/3 lift is generated. Okay, and it says about, obviously wings are different, but if you just have that ratio, you'll be about right. The other third of the lift is dynamic lift due to the angle of attack of the wing. So basically, literally, obviously, if you push the wing through the air impacts against it, and that in itself will generate a certain amount of lift. So you've got 2/3 from pressure reduction, 1/3 due to the angle of attack. Again, it's just those 2/3, 1/3 values that you'll need to know for the exam. But from a practical, from a flying point of view, it just gives you a better understanding of how the wing works. And we'll look at angle of attack and what that does to the wing a bit later on. Okay, good. So hopefully that's fairly straightforward. That is just more for advanced. You don't need to know that for, it's in there for extra information. You do not need to know it for the exam. Okay, what you do need to understand though is this concept of center of pressure, which for all of you, if you've ever done any sort of physics, applied math, anything, you'll be used to the idea of center of pressure, or center of force, where you basically sort of average all the forces acting on the wing, and you'll get, if you average out all the various vectors, you'll get a center of pressure. The relevance of this, I would suggest, hopefully you've all got a pilot handbook. Yes, yeah, good. There's a good explanation of in this of center of pressure and stuff, how it works, and how it affects pitch control and different things. So I'll go over it a little bit, but it's covered so well in the book that it's simpler just to go through it on that. But the main thing is that it's a principle you're operating with. Where is the center of pressure of the wing, and the relevance, which we'll come on to shortly, in terms of controlling the wing, is your position in terms of the center of pressure or center of force of where the wing is, and it's not constant. Depending on how the wing's moving, that the center of forces will change. But it's just this idea of what is the center of pressure, and it's just an average of all these forces. So I'm hopefully, if I'm going too fast, or so you have a question on, feel free to ask. But there are some other sort of more practical, technical bits that require a bit more time, and this is kind of data I can skip over to some degree. There are various definitions you need to know, and these are just definitions. And I think, what does it say? Be able to define and use terms such as the chord line, the angle of attack, aspect ratio, center of pressure, and it says washout on here, which we'll talk about briefly. So let's start with aspect ratio. But aspect ratio, you all fly wings. You're a paraglider pilot, so I'm guessing most of you probably know what the aspect ratio of your wing is. If you're on an A wing, it's probably 5.1 or something. B wings go probably from about 5, depending if it's a low B to a high B, anywhere from sort of 5.4 up to maybe 5.8, maybe 6, depending on the B. C wings, you're generally going from like sort of 6 through to 6.5, and then you'll get into sort of D wings, which will be in like 7 aspect ratios of some, probably more like 7 to 8. So an aspect ratio is quite simply that. It's the span of the wing divided by its chord, and the chord is the difference, the distance between the trailing edge and the leading edge. Keep it simple. So basically, that, as you probably noticed, the higher the aspect ratio, the thinner the wing. If you take a look at something like a sailplane, I don't know what, I mean, a sailplane wing probably got an aspect ratio of about 50 to 1, 60 to 1, something like that. Very long, very thin. So you get a very high aspect ratio. And it doesn't really go into much detail, but your kind of significance of it is the higher the aspect ratio for a wing, the more pilot input is required to fly it, basically. You take a low aspect ratio wing, you can stick a sack of potatoes on and shove it off a hill and it will fly quite happily. It's designed, school wings are designed so that you don't have to put a lot of input into it. It will self-correct. It's very stable. It's not going to fall out of the air easily. It's not going to get thrown around as much. It's designed that way. But then, because of that, it won't perform as well as a higher aspect ratio. So as you go up on aspect ratios, the wing requires more pilot input, but then you get more performance from it. But you only get more performance if you know how to fly the wing. So it's a trade-off. Anyway, that's kind of probably the most significant about aspect ratios. Again, the rest are just definitions. They're easy to look up. I'm not going to spend too much time on that. Again, there's a section here just on various things. So aspect ratio we looked at. Angle of attack is probably the key one to understand. And it's the angle between the chord line and the airflow. So you've got your wing shape, you've got your air approaching it. So if you put brakes on more, then you are increasing the angle of attack. Yeah, you're basically, if that's the front of the wing, trailing edge, you apply brakes, the wing's going to basically, it does this. So you're increasing the angle of attack. Hands up, you bring this down, put speed bar on, it pulls it down a bit more. You're decreasing the angle of attack. You're causing the wing to go faster. In theory, up to a point, as you increase the angle of attack, you get more lift. As you decrease the angle of attack, you get less lift. But you're going faster. And that's something we'll look at a bit later as well. So really, of those ones, the two, angle of attack, aspect ratio, the two main things you need to know. The rest are in there because they need to be. But you don't really need them for the exam. Same like dihedral, you don't need to know that for the exam. It's just there. It's a flying term. Again, span is the main one we need to know, which is distance from wingtip to wingtip. That's it. That's the span of your wing. So span and chord gives you the aspect ratio. Tow out, don't worry about. Washout. It does mention in the syllabus you should understand what washout is. Washout is easiest to see on a hang glider. As I said, washout is twist that's built into the wing. So again, it describes it and gives a diagram in here. Basically, the end of the wing, there's like a twist. If you look at hang gliders, you'll see they're not flat. They've got a twist at the end, and that's the washout. And it basically, as it said, it's this bit here. It basically means that because of the washout, if excess pitch is applied, then the tips will stall after the center, and so will provide a nose lowering effect to encourage return to normal flight. So it's basically an aerodynamic thing to stop a hang glider from just bouncing to the ground nose first. It basically causes the airflow, it causes it to try and drop it, it will change the stall effect and bring it back into level flight. It's not, paragliders have washout, I don't think they do. Yeah, so it's more to do with hang gliders than paragliders. Center of pressure we talked about, and then what we will, the other term, the final term here is this, which is lift drag, LD. It's the lift drag ratio, which is the ratio of lift. We're going to cover lift and drag a bit later, but the main thing is that the lift drag ratio is the same as your glide ratio. So if the lift to drag is 10 to 1, the glide will be 10 to 1. In other words, you will go, for every 10 meters you travel, you'll drop a meter. That's obviously quite theoretical. It assumes you're flying in smooth air with no lift, with no sink, and no other things going on. So, but the main thing is lift drag, glide ratio, same thing. That's the key thing you need to know about that. Basic wing geometry, again, it's to do with aircraft, isn't how paragliders balance. So I'm not going to go into too much detail. Again, you've got main thing this one shows is on this diagram here of the wing itself is the chord length between the front, the leading edge, the trailing edge. That distance is the chord, and it quite nicely shows the angle of attack on this diagram as well. That's the main thing for that. The wing thing, as I say, we're not flying aircraft, we're not flying planes with fixed wings, so you don't need to know how the way the wings move keeps the plane stable. So I wouldn't worry too much about that. But this is more this diagram here. So that's the next bit is to do with instruments, and this piece of data that 1 millibar, a change of 1 millibar equals a change in height of 30 feet. It's one of these pieces of data that you just need to know. It will come up in the exam. There'll be questions which will address that fact. But yeah, you need to know 1 millibar, 30 feet. If you work in metric, what's that? But that's probably easier in metric. I guess if you work in metric, it's about 10 meters, isn't it? So it's like 1 millibar, 10 meters. But you'll generally find it's in feet. So 1 millibar, 30 feet. This is because we're dealing with instruments. This actually comes up on one of the other. I think this comes up on it comes up on another section. Air law navigation. But I throw it in this because if you've got an instrument, you will have these. You won't necessarily. Oops. Phil. Go on, Phil. Wait, what? So basically, if you have on your instrument the 2 settings which you may or may not, you probably don't call them QFE and QNH. Q stands for query, FE is field elevation, NH is nautical height, I believe. No, not field elevation, nautical height, nautical elevation. Basically, QFE is where you set at takeoff, you set your altimeter to 0. So then the readings you get from it tell you how high you are above the landing field. You might find that useful. It's a lot of altimeters will actually give you the option for displaying both. It is only relevant, obviously, to where you take off from. This is why it may or may not be that relevant. You know, if you set it to 0 at the top of the dike, it tells you how high you are above the dike. It doesn't tell you how high you are above the landing field. If you set your actual height on your Vario, let's say say 680 feet, and you go, okay, my height is 680 feet. What you're actually doing is then setting your Vario to the correct pressure for the day. Because you're basically, it is 680 feet, therefore it will now adjust the pressure setting so that it's correct. That's the main thing. Q&A we talk about in the other one, but it's in there just for reference. Q&A is standard pressure setting. It's the international standard 1013.2 millibars at sea level. Regardless of what pressure is, that's what aircraft set themselves on. Okay, nothing really to do with paragliding. Well, it actually does have a relevance. It does have a relevance. So aircraft will use 1013 or QNE for flight levels. So aircraft coming in like just above the dike, we're at FL 55, which is 5,500 feet. Now, if they are still on QNE, which they may not be, because they may be in transition, being controlled by the radio tower, but if they were, then they're working on 1013.2 sea level pressure, which probably isn't the pressure for that day. So they're actually coming in at, as far as they're concerned, at 5,500. It could be quite a bit of variance in that. You know, if you've got 30 feet per millibar, if it was like if the air pressure was actually 1,000 millibars, not unreal. That's 13 times 30. That's like there'll be a 400-foot difference in what you think they're at and what they think they're at. So you do have to be careful when you approach airspace, because you're probably almost certainly working on actual height. Like you're going, well, my actual height is 5,000 feet. You know, I'm not at 5.5, but the plane isn't working on actual height; it's working on QNE. So do bear that in mind if you approach airspace and leave a big enough margin. You know, we normally say leave at least 5. Don't get within 500 or 600 feet of airspace, so that you've got a margin of error to avoid getting into it. So you don't sort of try and sort of scrape it. Go, well, I just got up to, you know, 5,499 and miss it by 12 inches. Bad idea. Really bad idea. Aircraft are big, you're small, you don't stand a chance. So anyway, so it's not a lot to do. It's not exactly a flight theory, but it's worth pointing out. Where are we? Now, I've got a little diagram here which just gives you various examples of QFE and QNH. You know, QFE here, airfield 0, aircraft above it will be its basic height above the airfield. QNH will be its height above sea level, etc. So it's I say it's more just to do with how you set your instrument up and understanding those two terms. Right. So Vario. What do you need to know about Vario? So the syllabus says, understand the basic working principles of altimeters and variometers. That's all. It's basic working principles. So the basic working principle is it's a device for measuring the rate of change of altitude. It achieves this by measuring the rate of change of air pressure. There are, it's basically, so at its very simplest, we don't carry these, we carry electronic things to keep the weight down. So basically, at its very simplest, it need only consist of an enclosed volume of air and a pair of pith ball flow meters, so that the balls meters go up and down. One measuring air entering, one leaving, and it'll basically, as the air comes in and out, they'll move up and down. They'll tell you whether you're going up or down, just by changing air pressure. Fortunately, we don't carry those with us. Instead, there'll be a little piece of electronic equipment, a pressure transducer, which converts the change in pressure to some form of charge, usually some sort of resistance, and then it'll register that. You'll hear a beep or a squirk or a squeal or whatever noise you've got it set to. The electronic circuitry converts this change to a change in voltage, which triggers the now familiar beeping. So that's all it is basically. So Vario is something which measures pressure sensitivity and alerts you whether you're going up or going down by the noise on your Vario. Traditionally, going up you'll get this beep, 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 and going down you'll get some sort of going down, horrible sound, going up, good sound. To be honest, you don't need to know much more about it. I think that's about as basic as you need to get it. God. They throw this in, and it's one of these things where at some point they just need to revise the syllabus and take it out. Nobody needs to know what a Netto or air mass variometer is. So it might be relevant if you were a sailplane or something, or an aircraft. We're neither. So it's in there, it's a definition, read it, forget it, you'll be fine. Again, a total energy variometer, we don't need to know about. It's to do with, again, it's to do with sailplanes, and if anyone's ever flown a sailplane, they'll probably go, oh yes, I know what total energy vario is. And in sailplane you get something called a stick thermal. What's a stick thermal? A stick thermal is basically an illusion that the glider is climbing in a thermal, when in fact it's simply the upward movement of the glider caused by nothing more than pulling the stick back, pulling back from the control stick, causing the aircraft to climb. So it feels like you're going up, so you think, oh, I'm in a thermal. No, you're not. You pull the stick back. Obviously, we don't have a stick to pull back on our wings, so stick thermals together. I guess if you are a paramotor, you kind of have, if you accelerate the motor, it will drive you forward. You'll get this little bit of a push. But it's to do with sailplane. So yeah, so that's more to do with sailplanes. If you're into sailplanes, great. If you're not, you can ignore it. Ignore that. It's just there for reference. Okay, so we're back to getting something slightly more chunky. Any questions so far before I do the next bit? If you do, just unmute yourself and ask. Brilliant. So, polar curves. So we're going to look at what a polar curve is. We're going to look at the principles of it. You will get questions on this in the exam. You will actually get a polar curve, and you will be asked to draw lines on it and work things out. Once you have the basic principles, they're really straightforward. So I'm going to go over it enough that you've got those basic principles, and then in the exam it's a double. But we'll also look at the practical side of it and how it relates to your flying. I don't know any pilot who actually knows what the polar curve for his wing is, so it's the principle of it, rather than knowing, well, my polar curve looks like this. It's the principle of speeding up, slowing down, min sync, and things like that which we'll cover. So basically, a polar curve is simply a graph of the forward speed versus the vertical speed of a glider. So in theory, you could work out your polar curve by measuring again, if you took absolutely still air and you worked out as you increase your speed, what happens to your vertical speed, you get a polar curve. So going across the top, we have airspeed, in this case in knots. Down the side, we have sync. Back, it could be knots, it could be, as long as they're in the same meters per second, feet, it doesn't matter what that is. It doesn't have to be knots, it could be feet per second. I think this is in knots because I stole these diagrams from a sailplane site because they were quite useful. So you can replace knots with meters per second, feet per second, as you wish. So our polar curve is this, is the curve that's running around here. Now, if you then take basically the top of the highest point of the curve, that is your min sync. It has to be. It's the minimum sync. It's the minimum. Anything to the left is increasing sync. Anything to the right is increasing sync. So min sync is this point. So if we run that up, we'll get the airspeed at which you get min sync. Okay, is that totally straightforward? Yeah, it's quite simple. It's the peak of the graph. Go to the top. That will give you your speed for min sync. Now, to get your best glide ratio, so remember, glide speed, glide and lift drag, same ratio. So, and this is worth going over, because a lot of people think, well, surely min sync will give me my best glide. No, min sync doesn't give you your best glide. So to get your best glide, basically, assuming you've got a polar curve, it's if you take the line from the origin, which just touches the curve, which for those who remember their mathematics is the tangent, but it's basically where you take a line from the 0 point, draw it to where it touches your curve. That, when you take it up, gives you your best glide speed. Now you'll notice that is not min sync. Min sync is back here. Best glide is this. This will get you to where you want to get to in the most optimum way, basically. So it's a I think some of the way I describe people is this: if you've been out flying, say like you'd often see at Devil's Start, you see pilots take off, but certainly recently the wind is very strong, and they're not going anywhere. They're just gale hanging. Literally, if they look down, they'd be above exactly the same spot. Now, if they were on min sync, they'd quite happily stay above that spot for some time. They're not going forward. If they increase their speed, they will actually now be on a glide to get somewhere. And that's essentially what's happening. Is min sync is you're hanging back. Best glide is giving you a better progression forward. But that's how you work them out, basically. So min sync at the top, best glide where this line touches the curve. Now, so this is an interesting point. I'll just split back to this one. So here, show more weight. Basically, when you add, one of the things is what happens if you add weight. So when you add more weight, you go faster. But the polar curve doesn't change shape. So bizarrely, your lift drag ratio actually stays the same. So you don't affect the glide, but you do increase the speed on that glide. It's often why you'll see competition pilots will carry extra ballast. They'll increase their weight to get that speed. If they know it's not changing, that their glide is the same, so they're going to arrive at their destination faster on the same glide angle. Now, a lot of people go, I don't think that's true. It is true. So the key thing is that if you add weight, you speed up, but you do not change the lift drag ratio stays the same. Okay. So basically what you need to know is how do we, sorry, we'll go back one step. So this best lies on the assumption that you're in still air and the air is not rising, the air is not sinking. Okay, so there's no headwind, no tailwind, no sink, no lift. So what happens if you do have those? How do you adjust for it? So basically, if you're in sinking air, then you move your So if it's if you're in sync of 3 meters per second, you would take, instead of getting your glide angle from the 0 point, you go up 3. Draw your line so it touches, and this will obviously, because it's further up when you draw the line down, instead of meeting here at 40, for this diagram, it's now here at 60. So basically it's saying in sinking air, you need to go much faster to get the same lift glide, to be on the best glide. Which is why you often hear fly fast through sinking air. It's not just because you want to get through the sinking air quicker. It's actually because it gives you your best glide through it. So yes, you're going through it quicker, but it actually increases you get your better glide. So that's why you'll get this thing of sinking air, go fast. So after that, so by sinking air, you go however many meters per second, you go up the y-axis vertically and draw your line down. So basically, for a headwind, you basically do the opposite. So basically, if you're in a headwind, then you move your origin to the right. Okay, so if you've got 10 meters per second, 10 knots headwind, then you would move your origin point over by 10, so you can see it shifted here. And now you draw your line. So again, it's going to increase the speed you need to fly for best glide, which makes sense. It's like the wind's now blowing. You're in a headwind. You need to fly faster to maintain best glide. Right? So when you get one of these diagrams, they might say you're in sinking air in a headwind of 20 knots. So you're in sinking air of 2 meters per second in a headwind of 20 knots. What's your best glide? So you go right. So I'd go up 2. I'd go across 20, and then from this point, from 20, I'd then draw a line down so it touches the curve, and I'll find out what my airspeed should be. Yeah, it's as straightforward as that. Conversely, so it's just it's the same thing again. It's just explaining offset the polar curve by the rate of climb expected, and whatever headwind you're flying into. So this is a little diagram showing with increased weight. So so here we have our light. So the base of the polar curve, what happens is the polar curve doesn't change shape, it just shifts because of the extra weight. But the actual glide, you'll notice, it basically is the same glide angle. It's just you're going faster to get that same glide. So yes, so if you're in competitions, then that gives you an advantage. If you're not in competition, I mean, I guess the other practical point from you guys is in terms of where you are in the weight range on your wing. If you're quite low, if you're at the bottom of your weight range, then your best glide speed is going to be it's going to be slower than if you're at the top of the weight range. Which will probably explain why, if you're at the bottom in stronger winds, you have difficulty because as soon as you you go on bar, increase the speed, you're no longer on your best glide, and so you sink much faster. Whereas someone who's heavier on their wing can actually be on best glide on a higher speed. So they will actually do better in stronger conditions. weirdly, or maybe not so weird. Anyway, so basically that's that's polar curve. That's all you need to know about them. You don't see any more complex than that. As long as you know how to shift the origin up and down, draw your lines, you can handle all the polar curve stuff.
John, can I just ask you a question about what you said then?
Yes, please do.
So if I look at the graph, it seems to me that the heavier glide speed has greater sink. So for the heavy polar, he's got more sink and he's covering the ground faster, but he's going down just as far, isn't he?
Well, your glide ratio is the same. Bear in mind, this is to do with you're traveling faster through it at the same. It's the same glide angle, so you're still going down the same. You're going down this line. You're just going quicker.
Yeah.
So you are approaching the ground faster because you're going faster. Therefore, your ground speed is quicker. So you will get to the ground quicker. Your gamble is that you'll get through the sink faster. At the end of the sink, there'll be lift. So what you're gambling on, and if you actually diagram it all out, it's amazing how it works. But basically, yes, what you're aiming for is on the height with the extra weight, you will arrive faster, possibly lower, in the lift. So you might get there 10 seconds, depending on how far away it is. You might get there 10 seconds quicker.
So I'm exactly the middle of my weight range on my wing.
Right.
I'm being told I'm too light for the UK. I should be heavier.
Who's telling you that out of interest?
So I know that's not maybe a discussion from here, but is that something that we should consider in the UK, as being on the heavier side, be able to penetrate more because of our condition?
Well, it depends whether you fly. It depends how strong a condition you fly in. If you're flying in, we can get quite light conditions.
Yeah.
I think generally what they're saying is yes. If you're if you're launching from a mountain, you tend to launch in nil wind and forward launch. Doesn't mean you won't meet wind while you're in there. Being in the middle of the weight range is fine. It's not a problem. It really, in terms of your wing, it's only if you're at the bottom of the weight range, it becomes an issue.
So as a new pilot, I'm not going to fly in really strong conditions anyway, because I won't be able to ground handle and I'll scare myself shitless probably.
Yeah, probably.
Better off. Huh?
Yeah, probably. You can always stick an extra litre of water in the back. That'll wait out.
All right, thank you.
Yeah, no problem. No, but it's interesting to have a practice. Yeah, this is the theory, and it's interesting to look at what it means. Let's say you should only really be concerned if you're right at the bottom of the weight range of your wing, because you will find it harder to fly. You will find it flaps around more. You won't feel quite so in control of it. You'll find it harder to turn. It won't be as dynamic. There's various things on that you should. So nobody really recommends you fly at the bottom of your weight range.
No.
So I always fly near the top. I just get wings where I'm within a few kilos of the top of the weight range. Doesn't seem to stop me going up. So,
okay, all right, thank you.
No problem. Cool. I mentioned these very quickly. McCready ring, again, sailplanes use them anymore. It was basically a way of adjusting, of working out speed supply, using the sync. By working out the sync, you can see I got sync is this. You'd adjust this ring. It said, "Oh, my airspeed needs to do this." We don't use them on paragliders, but it may come up. It's worth knowing what they are, and it was literally a physical thing stuck on the panel, so you could work out how fast to fly for optimum, for max glide. All right, that's out of it. Okay, so forces on a wing, or forces on a falling object. So basically, resistance or drag is the square of velocity. So as you speed up, resistance increases proportionally by the square of it. If drag is equal to weight, i.e. it's in equilibrium, then acceleration is 0. It doesn't mean it's not falling, it just means it's not accelerating. And that's kind of important to know. You know, this is where you get this term terminal velocity. If you throw something off a building, initially its weight will exceed the drag, so it will accelerate, build up speed, and then because it's increasing in speed, drag is going up by the square of the speed, and then that will eventually balance the weight, and it will no longer accelerate. It will still fall, but it will now fall at a constant velocity. That's where you get the term terminal velocity. Just a bit of background. What you need to know is the following. So there are two types of drag that you'll run into. The first is parasitic. So parasitic drag is due to skin friction, the shape of your body, the lines, basically anything that's blocking the airflow. So parasitic drag is the one that increases as a square of the velocity. So this, if you look at this diagram, you've got the black dotted line. You can see it. So at low airspeed, parasitic drag is low, but it accelerates rapidly the faster you go. It's why sailplanes will have like really polished wing surfaces. They're trying to reduce the skin friction as much as possible, because they are going, you know, we're not traveling at 120 miles an hour. They are. So at those speeds, small changes in the smoothness and this that make a big difference. For paragliders, it's, you know, we're in this lower band. We're not, you know, occasionally you might be traveling at 60 kilometers an hour. It's not often. So it's a parasitic drag. Yes, it's a factor. It's not a huge factor. You know, so if you go out in a nice streamlined top compared to a slightly baggy one, it probably isn't going to make that much difference to your performance on a paraglider. There's enough other things that are doing that already. There will be some difference, but not a huge amount. And the other line on this, the red one, is induced. So induced drag, next, right. So induced drag is the byproduct of lift and increases as the angle of attack increases, i.e. as you slow the wing. So let's just go back on this one again. So here you can see that as you go faster, the induced drag drops. As you go slower, induced drag increases. And we're going to look at that in terms of wing stalls in a minute. And if you put the two together, you get the total, and this is your sort of, this middle curve of the solid black line is the general shape of drag to speed. So you can see that it increases. You can see how the effective drag, it reduces down, gets this low point. There is a minimum sort of drag point, and then it increases again. So you need to understand the key things on this is knowing the difference between parasitic and induced. Just give yourself examples, go through it in your head, whatever you need to do. When you see something and go, that's induced, that's parasitic, just get those totally squared away for yourself. They're very key to understand. All right. Okay, so stalling a wing. So why? Well, so we'll open this up a little bit of discussion. So earlier we looked at how a wing flies. A wing flies because of the airflow over the wing and it generating lift. So how do you stall a wing? What stalls it? Now, if I open this up to questions, most people say, well, you stall a wing by applying brakes or slowing it down. So my question is, why does that stall a wing? What is it about putting on the brakes that causes a wing to stall? Now, your stall wings, when you land, you brake hard, you collapse the back, the wing drops. If you've done SIV courses, you'll stall a wing in the air. You'll deliberately get to the point where you'll brake the wing, and it will suddenly collapse behind you. If you're unlucky enough to be in really rough, shitty air, your wing may have stalled and may have fallen behind you. Hopefully none of you experience that. It's quite an unnerving experience. But why? What stalls a wing? So if we take a look at this diagram, we can see you've got the front of the wing here, air flows over it, and at the tail of the wing, the wings we fly, none of them are perfectly aerodynamic. So you will get these little vortexes of air at the back of the wing. You'll get some turbulence at the back. As you increase the angle of attack, this turbulent air increases. That you're disrupting the flow more and more. So because you now have turbulent air flowing over the top surface, there is no lift. That's why a wing stalls. It's got nothing to do with the fact you're flying slowly or anything else. It's to do with increasing the angle of attack to a point where there is no airflow, so there is no lift. And it's important to understand that because it will help explain why, if you're flying in rougher air, you've already got more turbulence over the wing, so it will now stall at a higher speed, basically. It will stall with less brake in more turbulent air, because all we have to do, if the air is already slightly turbulent, and you increase the angle of attack and increase that turbulence, you can collapse a wing. And you'll get it to some degree. I mean, some of you have probably experienced a point where you just get asymmetric collapses, where one side of the wing goes. Basically, that side of the wing, it's no longer inflated. Why is it no longer inflated? Because the air going over the top of this edge of the wing is this turbulent air kills the airflow, kills the lift, so it collapses. And you know, we fly in thermic conditions. We're flying in airflows with air going up, air going down. We're moving between them. So you are going to fly through turbulent air. You are going to experience things where and it's not uncommon if you're not solidly in a thermal and you're sort of half in, half out, but wingtips go. You'll see wingtips go, flaps in, flaps out. And all that's happened is that you've hit some turbulent air. The surface pressure is you've got turbulence over the top of the wing, so there's no lift, so the wing collapses. It's as simple as that. You fly out of it, it goes bang, pop, and it pops back out again, and you're off you fly. So anyway, so the point is, so per the syllabus, you need to understand how a how a stall works. That's how a stall works. Portal glider, yeah. So next bit. Any questions on that, by the way? Are you all happy with that? Understand that basics of airflow and turbulence and stuff like that. Okay, cool. So forces on a glider: lift, drag, weight. Lift is what's pulling you upwards. Drag is what's pulling you backwards. Weight is what's driving you downwards. Now, and again, this is something that people sometimes struggle with, is that they're in equilibrium. The lift drag equals lift is equal lift and drag balance your weight, or the weight generates enough drag that it compensates the lift, whichever. You'll notice when you fly, that you're not accelerating up or accelerating down. You know, and given everything else is equal, you're at a constant speed. If you're at a constant speed, there is no acceleration. Because there's no acceleration, you must be in equilibrium. I mean, it's just basic physics. So yes, you might be falling all the time, but you're falling at a constant speed. So even though you're dropping, you are in equilibrium. The forces are balanced. So just make sure you understand that it's the forces are balanced, and lift drag then determines your glide angle. Yeah, so quite simply, what is lift to drag? It's the amount of lift generated by a wing divided by the drag. It's just those two things. And the glide ratio equals lift drag. So if you know glide ratio, you know lift drag. If you know lift drag, you know glide ratio, basically. Right, so the other thing that you need to know a little bit about, again, this covers it very well. So I won't go into too much, use that to revise. You need to know three terms: pitch, roll, and yaw. So pitch is this motion of your wing, roll is this motion, and yaw is this motion, like basically the side to side. I say I won't. The book explains it very well, but basically, paragliders, because you're effectively a pendulum and you're quite far below the wing, you automatically stabilize. In other words, if you swing back, if the air causes you to swing forward, because of the way the glider works and the force changes, it automatically swings you back and balances you out. You swing back, the same thing happens, the center of force changes, and you swing forward again. It's the same thing with the wing. If you try and roll your wing, like rock from side to side, it actually comes back. It comes back into equilibrium. Why? Because you're hanging underneath it. You roll this way, your weight shifts, your weight comes back.
John, are you waving your arms about or something? Because all we can see is the PowerPoint.
Oh, okay. Sorry. You're absolutely. I'll switch off PowerPoint. 1 second. Let me stop screen. Good point. I keep forgetting. I'm going to stop sharing the screen for a moment. Stop sharing. Put you back in screen. Right. Can you see me now?
Yep.
Cool. Well spotted. So, yeah. So basically, so pitch is backwards and forwards. Roll is side to side, and yaw is swinging around, basically. So paragliders, because of their center of force, if you go forward, your weight will pull the center of force of this changes. So rather than the whole wing just going, oh, I'll just tip you over, the center of force moves. You then swing back under, and it bounces out. The same if you swing back, center of force changes, you come forward. If you're on a roll, exactly the same thing. If you roll to the side, your weight goes to the side, gravity pulls you back, and that whole pendulum effect stabilizes the wing. So it's got its counter effects built in, basically. Again, have a look in the handbook explains it very well. Lots of nice diagrams, but it's kind of it's a pendulum. If you swing it, it swings back and it bounces out. And it's good from again, there's nothing directly to do with the exam, but from a flying point of view, it's good to know the wing will self-correct, because if you find you're actually getting in trouble, things are going wrong, you don't quite know what to do, generally your best option is do nothing. The wings you fly will sort themselves out. The best thing you can do is hands up, wait, watch what the wing does. I mean, I'm not saying that's the only thing you should ever do, but if you don't know what else to do, that will probably save you. It's when the thing that, because the wing is trying to correct itself, what usually happens is if you don't know exactly how to handle it, what pilots do is they inevitably correct wrong. Like the wing's going one way, and they pull the wrong side. They make the collapse work. They make the whole thing go worse. So if it's really going shit, you don't want to do the wing, hands up, it'll probably sort itself out. But having said that, as early as possible, do an SID course and find out exactly how your wing works. They're great fun. So I'm just going to quickly check through. That, believe it or not, is flight theory instruments. That's everything you need to know. So what I'll do now is I'm gonna let's stop recording. I'll keep recording a bit. So questions. Anyone got any questions on any of these points? Fire away. If you don't, that's brilliant. I've done a brilliant job.
So I've got a question.
Yeah.
Must be a pain. So on a paraglider, you're talking about the stall point and the fact that the wing's angle of attack increases.
Yes.
You're pulling actually the brakes down, aren't you? So your A lines and B lines are still holding the front of the wing level. And effectively, aren't you decreasing the lift on the wing because you're increasing the profile of it by pulling the brakes to make it a more round profile?
So, what you're doing is you're increasing the angle of attack.
Okay, by pulling the brakes.
So
because they're rotating around the B lines, are they?
The
C
lines. It'll be the center of force that's actually rotating around. I mean, you're pulling down the C. You're pulling down the C, so the wing is basically doing this.
Yeah.
Pulling the back down. You're increasing the angle of attack, so you will get this initial effect of lift, bizarrely.
Yeah.
But what you're losing is, because you're now increasing the angle of attack, the turbulence over the wing is increasing.
Yeah.
You're losing that 2/3.
Using that, lifting up the 2/3. Yeah.
Yeah. The angle of attack accounts for up to 1/3. This accounts for 2/3. So if you kill this, you've lost 2/3 of the lift.
Yeah. Okay. Yeah, no, that makes sense. I just couldn't try to picture the shape of the paraglider in my head when you're putting the lines. The brake lines are effectively attached right to the back. So
what I would suggest is, next time you're on the hill, watch people as they brake.
Yeah.
Watch the wings. Watch what actually happens to the profile. It's not quite a rotational thing.
Exactly.
You are changing the shape of the wing.
Yeah.
Watch what happens. When you do it. Not that they rotate. You're actually if you haven't changed. You're right. A and B lines don't change length. You're shortening the C's. You're basically pulling that trailing edge down.
Yeah, exactly.
So you're changing its shape.
Yeah. Okay. All right. Thank you.
Yeah. Any more?
Very quick one, John. You talked about your pitch and roll stability. How about your stability?
It's actually kind of built in. It's when you apply one brake, you're actually inducing yaw. If you think about it, you're slowing down one side. The wing will now start to turn. As it turns, it will actually adjust itself and try to go back to level flight. So paragliders are actually very good at handling that yaw. I mean, try it. Try swinging from side to side. It's bloody difficult. You don't. You've got nothing really to kind of work with. I mean, the only actual way to do it effectively, you have to grab the lines and twist them to spin yourself around. But that's you spinning, not the paraglider. Bear in mind. To actually get the way you induce yaw is brake. You pull down one of the brakes, slows that part of the wing. This part speeds up. As it comes around, it then goes back into level flight again. You can try it. So basically, you brake, let it go. It levels itself off very rapidly. Partly because, again, as you turn, you've swung out slightly, you swing in underneath again. That levels the wing out. it's all to do with the pendulum effect, and they're actually very good at handling yaw, bizarrely. They work well at that.
Yeah, back in the day, I used to fly hang gliders, and the sweep back
Okay,
gives
yeah.
you more stability. So your natural sweep on the hang glider makes you point directly, and kind of levels out that yaw.
Yes, that's the design. So to make that work, that's why so wing design comes into that, because you don't have the same. So you don't have the same pendulum effect because you're sitting right. You're underneath. You're right next to the wing. So hang gliders, paraglide, very different physics. You know, paraglider, you've got all this. You've got this space. You're down here. Hang glider, you're here. So the wings are then designed to handle that. You know, to stop people just stalling out the sky, basically. Whoa! Yeah. The paragliders are very good for that. I mean, it's they actually, as a flying machine, they're very good at correcting themselves and keeping you on level flight, assuming the air's okay. Okay, cool. Good. Any other questions? So it's not, you know, it's not a super complex topic. Go through the data, do your studies, and what I'll do, I'm going to talk some other bits. I'm just going to